your talk. Thank you very much.
Great, thank you so much. So yeah, I guess we brought a few Google services down the first time, and I was actually about to get to the point of a break, which so the timing is not or wasn't super bad. The break has been definitely longer than what I was intending. Instead of 10 minutes, it's been like more than 24 hours, but here we are. So maybe just to kind of get you back into context, we're going through a journey that brought us from AlphaGo to AlphaStar and beyond. And we just were concluding, explaining, and reviewing technical aspects of AlphaGo and AlphaZero. And I was presenting you with this kind of updated table where we're going to build up a couple of more models, and was telling you how AlphaGo is a model-based reinforcement learning approach that can, in principle, only be applied on two deterministic environments, and also uses the ground truth model to model the transitions in the tree search. And it's a model-based approach because it actually uses this idea of search and planning to improve upon a base policy through searching, expanding, and reevaluating positions further along the game. So now we're back from the break. I don't know if there are any questions about the algorithm or its connections with other model-based reinforcement learning. Otherwise, we're going to move forward in time as we go from 2016 to 2017, 18, and 19, where we developed AlphaStar. But let me just briefly pause to see whether there are any questions, clarifying points from both MCTS, AlphaGo, or model-based in general. I'll pause for, again, a sip of my tea. Now it's actually properly tea time in the UK. Great. So let's move forward. And as we sort of cracked the game of Go, another project, and in fact, the company that builds this real-time strategy game called StarCraft, almost on Twitter actually said, hey, maybe it's time to play this fairly complex game. And it was quite timely because this is a game that both I played. Actually, I was at UPC, I was playing quite a bit of StarCraft. And also during my PhD at Berkeley, also I was part of a team that built a bot that was mostly based on rules, etc. And of course, it was regarded by AI competitions as a very tough challenge where even the best agents that people build, even when not restricting the agent's capabilities, they were novice at best at playing the game of StarCraft. So it felt quite difficult to go about playing this game. And this was an exciting moment because we just had built, with MCTS planning and AlphaGo, we had built this incredible model-based algorithm that we were hoping we could just simply apply to now every domain. And there are actually very good reasons for which a game like StarCraft, which for those who are not familiar, looks a bit like this when you zoom out. This is a zoomed out view of the whole map. And it's a game that involves, building new expansions, right? You're spawned here. You have a few units. You can go around in the map. You get more resources by expanding. Also, you build units to engage with the opponent, to see what the opponent is up to. Unlike chess, you don't see the board all the time. You must be at the positions where you want to gather information from. And obviously, it's quite complicated. The action space is very large, et cetera, et cetera. So it is a very fun game to play, played by many professionals for many years, actually. It's called esports because it's really played as seriously as sports. And as I was saying, this game involves a few levels of decisions that you would think, and we as humans, as players, we certainly use some form of model-based planning as to play the game perfectly. The first aspect is called macro management, which involves these economic sort of decisions about whether you should expand or not, or you should just focus on building a good set of units to counter or attack the opponent. And also, you need to decide what kind of units are you going to invest in based on what you've seen from the opponent. You try to counter their unit. It's a bit of rock, paper, scissors as well, but in super complex dynamics, continuous rather than turn taking. So a lot of people have to plan ahead, thinking what is going on in the game, so as to plan these macro management decisions optimally. Also, there are engagements, right, like the actual combat, where it involves a lot of decisions, micro decisions about moving units, retreating, casting a spell on a friendly unit or on an enemy unit, blocking a choke point, etc. And all these decisions, generally, you do it based on probably some sort of model of what if I did this, what if I did that. And as a human, you play very quickly, deciding all these things, obviously, in real time. And in fact, all the bots that people have invested in StarCraft, or at least many of them before AlphaStar, actually used a small model of combat to simulate the outcome of engagements, so as to decide for a bot whether they should engage or not, right? So these bots usually are compounded of many complex pieces, and one of which is actually a model of engagement of who is going to win this scenario. It's not perfect because it simplifies many aspects of engaging, but it's actually used by many agents prior to us. So that sounds great. We should really start thinking about model-based, planning ahead, thinking ahead, both at the micro and at the macro management level. But there are many buts, given what I just told you about AlphaGo. First is that simulating the game is very expensive. We cannot possibly simulate the game at runtime. And also, there's also the opponent that we must play as, which we don't see. So it's fairly difficult to do that. Mu0 is a solution, which I'll describe in the last part of the talk. As I was saying, partial observability and dealing with uncertainty is quite difficult. Actions have long time span, which we're talking about thousands of steps instead of maybe 10 or 100 steps, such as in the games of chess, Go, Shogi that AlphaZero was so successful at. And of course, the branching factor is actually much larger than Go. Each action here is composed of a keyboard-mouse combination, which is far larger than tens or hundreds of actions of moving in a discrete board of Go or chess. So all these were good reasons not to attempt or just to give it a try, but really not having a lot of hope for the vanilla MCTS AlphaGo algorithms to work on a complex game such as StarCraft. And as I was saying, and I'm not going to describe these in detail here, but there are many other challenges about strategies and attractors of maybe a very narrow strategy that wouldn't be very good at covering all the possible StarCraft strategies that self-play gets stuck into. And that was the last part, which is the AlphaStar League, which I'm not going to describe. Today, I'll just explain you a bit about how AlphaStar is a model-free approach rather than model-based, but also how to make a model-free approach work on such complex environment, which eventually unlocked the performance that we saw about a year ago, actually now. So even though we attempted, but it was very hard to make model-based planning work in StarCraft, even playing the game itself has complications, especially around the combinatorial action space. So in a nutshell, and this is maybe a bit of like a reinforcement learning 101 guideline for anyone who wishes to start on a new project. In reinforcement learning, you need to think about the state space or the observations. Those generally are important, and they could be RGB pixels or all sorts of inputs, real valued images, etc. But the actions here were completely new in that we never attempted an RL environment that had an action space that instead of being select one action out of n, where n is like 100, this actually was building an action, a bit like building maybe an API call onto a very complex game. And this is actually what the API of the StarCraft engine requires you to issue if you want to talk to the game engine to issue an action, right? You need to decide action type, which units are selected, what's the target, if this is a queued action or not queued, if you're repeating this action, if you're delaying, what's the delay until the next action you want to issue. And all these actually are defined by Blizzard. This is not something we designed. This is a game that exists. It happens through network interfaces, in this case, not neural networks, but the actual networks that communicate between two PCs. And these kind of actions are sent all the time back and forward between the clients of the games that are being played. And we just said, okay, that is the action space we need to generate. And to do that, we took one of my favorite parts really of not really reinforcement learning here, but deep learning, which is a talk that I've given in other occasions. I call this the deep learning toolbox. So, you know, you're a researcher, you have a few inputs, right? The signals from the game, such as the minimap, which is an image, entities, which is a set of units that you own and that you see from the opponent, scalar features like the time or how many minerals do you have. And at the output, you must produce this structured data structure, basically, that signifies or defines an action, which is composed with several sub-actions that are quite complicated. For instance, the target point on the map, it's actually 256 by 256, right? It's not, I mean, in Go, it's 19 by 19. The map is fairly discretized. In StarCraft, we discretize it still very coarsely. 256 is not a lot if you play the game. You cannot click very precisely, but it's what we kind of deemed reasonable for AlphaStar. And once you have this input-output, you pick components. And for AlphaStar, we picked mostly standard components, obviously fit for the kinds of data that we were embedding from and to. For instance, we took MLPs for embedding vectors. We took transformers to embed sets. And we took residual neural networks to embed images. And then we use an LSTM as a memory module because you must remember what happened in the game thus far. And then at the output space, at the action part, we actually use the very well-known chain rule of probability to pick every single action at one time step, right? So for a single time step, we also have a small recurrence over the action or the sub-action type that picks the action type. Given the action type, then picks the delay. These are softmaxes. And then perhaps the ones that are slightly novel in how we use them are that we must pick a subset of units to which we want to apply an action. And for that, we use a recurrent pointer network, which is still a fairly standard element from any deep learning toolbox. And tuning these, finding the right shapes to connect this architecture, this is literally an architecture that you architect as a researcher. That was what actually made the approach that was successful from non-successful to successful in terms of getting the agent to really start playing the game in a believable way. There are many details and many advances further than that, like a distillation from supervised learning or the AlphaStar leak that made the agent more robust. But this was actually the core of the architecture. And this is actually what the agent is. There's nothing else. The game sends you an observation, you send an action back, and there are no handcrafted anything beyond interpreting the input and recasting it to the protobuffer that you send through the network, in this case, the actual network interface to the game client to say, hey, this is what I'm going to play next. So just for fun, one thing that becomes key here is imitation learning. And this is what happens if you actually train an agent purely from self-play. And what happens is kind of the obvious thing in hindsight, which is the agent gets stuck into this strategy that is very greedy, that is sending all its workers, these probes, to the enemy base and just attacking and actually winning this game. This is against the most difficult AI present in the game. Of course, this is a form of exploit almost, but it's still successful at beating the AI that Blizzard puts in the game. But the main problem there, unlike AlphaZero especially, it was that without human knowledge, the exploration of the strategy space in AlphaStar was just too large for us to find any reasonable strategy that did not involve. Imagine if you start randomly clicking, the successful strategies will look not great. in the game of Go and in AlphaGo, because you have search, you get a very random looking, very bad game, but MCTS actually helps you slightly improve that game. MCTS is a great inductive bias for games that involves deep planning like Go or chess to produce better policies. In StarCraft, we didn't know how to do that without massively handcrafting and saying, oh, you must collect more minerals or things that we didn't want to do. So instead, we relied on actually a lot of data coming from human games. And this is actually an extremely cool data set that Blizzard released for anyone to use. It's about 1 million games of StarCraft at any sort of skill level. What's very cool about imitation learning, which is a fancy way to say supervised learning, that's really what you do. You just train an agent to play StarCraft like you would train a language model to produce words or actions in this case, which are these fancy words of what an action is. And it's very interesting to see, for instance, that you can input to the agent the level of skill that the humans were playing for a particular game. And once you've trained this agent, you can request it to play like a professional or like a novice player. And it really actually plays like you tell it to play, which is very interesting to see. It would play the game not so well. It would get rich, but having money is useless in StarCraft. You need to invest your economy, etc. So this was actually the key that unlocked, instead of planning, that unlocked this interesting improvement over the initial policies, which then later produced the agents eventually with reinforcement learning. And what was very cool, a cool moment in the project was to just visualize an agent that was simply trying to imitate human actions with this interesting architecture. And this is the first-person view of the agent. You can see the agent has 3 bases. It's expanding here. It's moving its units over here to perhaps engage. It's now building a 5th expansion. And this looked like someone could be playing StarCraft, but it was actually our agents simply trying to imitate. Much like you see nowadays with the GPT language models, agents trying to imitate, writing human language. So it was very cool to see this. This was a very key moment, perhaps in early 2018, really, that we got these first results. And then we still had a few other things algorithmically that I don't have time today to explain, but they are all in the Nature paper. And of course, I'm very happy to discuss this with you any other time or offline. As I said, all these other details you can find in the paper. And the TLDR is that even the supervised agent is actually better than most human players. It's above 80% percentile of all humans that play online competitively on Battle.net. And then, of course, reinforcement learning is a sort of a cherry on the cake. It's a fairly big cherry because it boosts your performance from 4,000 MMR, which is good, but it's not great. I mean, it would lose against humans, professionals all the time, to this level that we reached thanks to further techniques. But the cool thing is this is a model-free algorithm, right? So going back to this chart, we simply used standard reinforcement learning and a feed-forward network. It has memory because you must remember past actions and observations in this game. And obviously, we used a lot of human data to sort of leverage or improve the policy a lot for free, whereas in other domains, such as Go, as I was saying, perhaps the search itself is such a strong inductive bias that you might not need this human data after all. But I strongly believe that for StarCraft, not using any human knowledge would be quite hard, and using it through in the way of imitation learning was actually quite natural, since Blizzard was very keen actually to provide an anonymized data set, probably one of the largest sequence modeling data sets out there, which actually is very cool. And I know many other folks are also doing research nowadays on this very cool domain. So I'll spend the last few minutes to discuss how would you go about, okay, like, look, I mean, model free is great. You did AlphaStar fully without a model, a plan, although humans are believed to use plans in the game of StarCraft, especially if you talk to anyone or if you play the game, it's hard to believe you're just reacting to what's happening and playing intuitively, right? So let's actually go back to the drawing board and try to think how to improve MCTS or AlphaGo to deal with these more complex environments that are too expensive to use the simulators, etc. Before I dive into this, and I know in the last few 20 minutes or so, we can also have an open discussion if you want to talk about really anything else. But if you have a question right now about like both the connections between AlphaGo and these connections actually and AlphaStar or anything related to that project, now it's a good time. Of course, I'm happy to do that at the end, but again, I'm gonna drink a bit, and then if you have a question, please go ahead and ask.
Well, if you let me, just one question.
Yeah.
So you, what was the change from AlphaGo to AlphaStar? You said that obviously you go from a perfect game to an imperfect one. Yeah. And I also guess that you go from a discrete game to a continuous one, right? The main challenge is this one.
Yeah, I mean, the main challenge, in my opinion, is the action space is so large that a random agent, the probability of seeing any game that looks reasonable is super low in StarCraft. In Go is also very low, but if you play many games, you actually get to see some games that are reasonable. So I think the action space is a main challenge. And the other one is not even only that it's real time and it's imperfect information, but also that it's a bit more messy. It's asynchronous. Like it's really like a lot of things that you don't have control over. Whereas in Go, everything is turn-based, and as I'll explain now, everything is just perfect for these kind of algorithms that do min-max. Does that make sense?
Yeah. So, and you said that the key to unlock the good plays was to imitate, right? To imitate human players. Did you do that with well, you said the architecture, right? Like deep learning. So yeah. What were they learning? So were they learning the actions to take, or what was it?
So I would say that from the last time, AlphaGo initially was also imitation learning. So the policy did use data from human games. In this case, what you do is we just simply did the most basic algorithm in imitation learning, which is called behavioral cloning. But if you're more familiar with language modeling, it's essentially, let's say you see a full game that two humans played against each other. What you're gonna say is you're gonna take every observation for every time step that you have an action, and you're gonna feed that observation as in this LSTM model. For every time step, you feed the observation to the memory of your agent. And also you feed the action you took in that observation, which you observe because you're just observing humans playing the game. And then up to time t, you are inputting observation from 1 to t and action from 1 to t minus 1. Okay, and then the output of the network is action at time t. And this action happens to have sub-actions and sub-components, but it's essentially, if you disregard the observations, it's actually a sequence of actions that you produce autoregressive, like as if you were producing words, right? So you produce the action at time t, given all the previous actions, and also all the previous observations, which are important.
Yeah, so it follows like a natural language processing type of, okay.
Exactly. And I obviously love sequence modeling and language modeling, and I would be the one to believe that this approach could work in such a complex environment where if you make a mistake, how would it recover to play the game well? So I really thought it wouldn't work, but it would do something. And at some point, it worked so well that we even played against humans in the paper, in the evaluation we did. So it really actually surprised myself, because the main challenge here is if you produce a word that's out of place, or you miss a building, or there's something that happens that makes you push a bit away from the distribution, then recovering is a very important thing that you would want the agent to do. But if you rely purely on imitation, this recovery is actually quite much more challenging, because you never really played the game. You only imitated actions, and you're out of distribution. That's the classic challenge, actually, of imitation learning, which is another fascinating topic. But it's a very good question. So thanks for asking this. Any other questions about imitation or the setting that we followed? That is very common, and it's really like language modeling, but applied to actions, right, rather than to words.
I have a question regarding, you said that the pure RL baseline didn't work at all because it was very greedy.
Yeah.
I remember from the paper, I read it kind of a long time ago, so I don't fully remember, but I remember you had a league of agents, and each of them had a kind of a customized reward function, right? And that kind of diversified the approaches. Did you try that approach from scratch? I'm guessing it didn't work, it wouldn't work, but maybe it would got something interesting.
Yeah, I mean, anytime we tried, all these AlphaStar League always were seeded from the initial weights that you found through supervised learning. Anytime we tried from scratch, it really produced something extremely greedy and very, very sort of non-robust. And really one of the things that as you go online and you play, it's a bit of an adversarial, it's an adversarial environment. So you don't want to just play the game well in your own private league. You want to be robust against anything you might see. So it really was very hard for the pure self-play to become as robust as we wanted to be, because obviously we were just going to put these to play online against people that just had no clue what they were playing against, but obviously they know the game quite a bit, right? So that was quite a fun experiment actually to run. Great. These questions are great. I mean, we can always adapt a bit, like the contents. Like the last part is more of maybe quite more technical. Sadly, there was no time to put the paper online, but I want to just give you a glimpse of the kinds of research that you can follow up from these large projects. So really, if there's any other questions, ask now, or otherwise I'll carry on with the last bit of the talk. Great. Okay. So I hope you're convinced that despite model-based being great, especially on the trend of algorithms using tree search, MCTS, and AlphaGo style, there was a big, and there still really is a big gap to be applied to games that are real-time, asynchronous, that involve many time steps, and where the branching factor is just truly humongous, right? So the main challenge, however, I will say, is that we needed to run the simulator, which is completely not feasible in most environments. Even in Atari, running the simulator is actually quite expensive already. So that's one challenge from going back to MCTS. Another one is stochastic environments. It's actually quite, the way AlphaGo works, or MCTS, does not rely on an environment that random things can happen. And that actually creates catastrophic issues if you add stochasticity to the environment, as I'll try to convince you with a couple of experiments we did on this regard. Now, in this kind of two-player zero-sum games, you can always play as you and as the opponent. It creates these very nice self-play dynamics, but in general, you cannot possibly do that, right? If you're thinking of competing on a sort of robotics soccer competition, you design your own team, but the opposite team, even if they are the same kind of robot, you don't know what action space those robots were designed as. What you really see is what they're doing. You see the state of the world, but you're not controlling the actions of the opponent. And imagine if the robots were not even the same kind. I mean, there is actually a huge assumption being made where AlphaGo/MCTS is applied to two-player games, where there's a lot of symmetries and niceties actually that make the algorithm work quite well for the kinds of games that are quite vast and quite impressive that we've seen and love. And last but not least, partial observability is also something that appears in games like Stratego and of course StarCraft, and not something that AlphaGo can deal with very well. Last but not least, and this is maybe more of like a human prior or bias that we all use with or without knowledge, which is when we plan, we don't plan absolutely every micro movement of every muscle as I speak or as I move my hands or as I do anything. You plan sort of at levels of abstraction, which might be, well, look, I will be hungry after the talk, so okay, I'm gonna like ask, like, I don't know, get some food, which I am actually gonna get some food later today, and these are happening at different time granularities. Whereas for the most part, if you remember how Go works, you're planning over your action and the opponent action, and you're taking the actions, every single action as a something to branch on, and as a result, you cannot abstract kind of jumping ahead in the game and so on. It's just technically a bit hard to do, or to envision how to do that given the kinds of algorithms that we've seen. So one solution to the first problem, which is we need access to the ground truth environment, actually comes very much related to also language modeling. And it's actually a fairly simple change. For more details, I recommend you taking a look at the paper called mu0 that was posted about a year plus ago on Archive. But the main idea is, look, we can do tree search, okay? We can expand the root, take actions from the root, and then instead of needing to see the actual observation, right? So I take this action and I ask the environment, hey, how is this action gonna make the board look? You don't need to see the board. You can use a powerful recurrent neural network that condition on the action that you just sampled will hopefully produce internally a representation that will be useful to predict the sequence of values of states implicitly that you would be seeing without explicitly inputting those to the neural network, right? It's almost like in language modeling, you're producing one word at a time, but you don't really have an observation that is what you've written so far. I mean, if you know what word you're producing, that is what the state looks like. After adding the word, then the state looks like a sentence that now includes that word. So that's a bit of the idea behind mu0. It's extremely simple, but actually extremely effective. The same results that we saw where we needed to use the environment, now you can get all of the good results from AlphaGo or AlphaZero, but without need of environments. So I'm going to skip some details because, I mean, this probably is too much, and I really want to have more discussion time actually at the end. But I'll give you the idea, and the paper, when it's published, I'll send the link perhaps to the group. But let me actually, and I'm skipping a bit ahead, but I'm just actually going to give you the intuitive comparison of a few algorithms, both AlphaZero and mu0, and then the one we propose. And I'll try to give you sort of the high-level intuition of how it works. Details matter, but actually they're a bit boring, so let's skip them. So as I was saying, AlphaZero, okay, how it works. You plan over an action. I'm going to move, in this case, you can see the move is moving this piece. You ask the simulator, how is the board going to look like after this action that I'm taking? And then you are simulating the opponent that plays a different move. And then you ask the simulator again, hey, now, given this action, how things are going to look like. You input that back into the neural network, and you ask it to predict the next action. And at the same time, not only predicting actions, you predict also who is winning, because that's kind of the point. You're rolling the game forward so as to predict the winner more accurately as you see more moves being played, right? So AlphaZero is, in this kind of depiction, which might be actually more clear, uses the simulator that takes the action that your neural network is producing at every time step of the tree search. This is going inside of the tree. And then it's giving you the board state, the ST+1, ST+2, and so on. Now, mu0 does almost the same, but it actually does not need to see the board. Just by looking and knowing what action you took at every time step, by inputting back the action to a recurrent neural network, you create an internal, hopefully, transition model. It's a bit model-based, but also not really, because there's no modeling explicitly. So there is also a bit of a blurred line between model-based and model-free here. But mu0 crucially drops this assumption of needing access to the environment. But it still does a few annoying things, which is you need to plan over your actions and opponent actions, and it's this turn-based approach that games that don't have this property, they wouldn't be able to be applied to. And also, it's planning over every single action taken at every single step, right? So these are sort of still major assumptions made in the further sort of development of these kind of algorithms in mu0. Now, you could say, look, let's ignore that there's an opponent. Let's just plan over my own actions, right? So I'm just going to think where I'm going to move next. And then given the action I took, I'm just going to try to predict my next action. I'm ignoring that there's an environment. Let's ignore that the environment maybe is taking a move against me, and there might be stochasticity. Let's ignore all these and assume that, and we call this mu0 single, that it's a single game, a single player game, and the environment, we don't model anything in particular from it. And in fact, in the mu0 paper, that's precisely the mode they use to play Atari, because Atari is a single player game, but it's also generally fully observable and deterministic, which for which this style of planning actually also works well. But if you actually apply this style of planning to chess, as you will see in a second, it doesn't really work. So what we propose is the following, okay? Now, I haven't explained what this means, but in sort of high level, what we do is, as you even implement a reinforcement learning algorithm, you have an agent.step method that takes the observation and produces an action. And then you have an environment step method that takes the action and produces the next observation. So what we're going to plan over is precisely over agent or your actions, right? So you plan over these. But then instead of planning about opponent actions, you plan over what we call environment actions, right? So we say, well, look, after taking our action, the environment might do something stochastic, might do something adversarial. We really don't know. So we're going to try to produce a discrete action that is not tied to any real action from an agent, but rather from sort of modeling the state transitions of the environment. And then we're going to plan repeatedly over our action, what happens in the environment, our action, what happens next, etc. And in this mode, the main question you might ask is, well, how do you train these, where does this purple thing come from? And that's the slides I skip. But in a nutshell, we use two pieces, two building blocks even from deep learning. One is a BQ vector quantized VAE. So we take trajectories, and what we do is we discretize states, right? So you have sequence of states. We discretize them. Instead of being like, I don't know, an image, we map them to a number via BQ VAE, which is a technique that you should read about if you're interested. But it's a very simple technique to discretize continuous or any domain, really. And once we have this sequence of discrete variables, now this is language modeling all over again, right? We have actions are discrete, and the discrete latents are discrete. So this is actually just applying the same principle that we apply to mu0. And it's almost like saying, hey, I'm planning over my action, and then I have a good model that from the discrete action that the environment is at, I'm going to know which next discrete action I'm going to observe. And you model that via the same laws as you use in mu0. And then that is what allows you to now be planning only over your actions and over whatever you model of the environment, which includes stochasticity, partial observability, etc. There is another mode of this where everything after taking your first action is controlled by this kind of sequence model of what happens on the state level of the environment, not at the action level at all. This is also a cool mode that we explored a bit in the paper that will be published fairly soon. And then if you do this, it's very easy to imagine that you could also jump and say, I'm just going to think about how in 6 discrete terms of the environment action interaction, where am I going to be in state space? And you can just train models that jump ahead, which there are many in terms of recurrent neural network architectures. We really haven't explored this, but the possibility of this jumpy planning exists. So this really unlocks a few possibilities, and I'm just gonna, and then you can do MCTS and all the usual things you would do using these pre-trained models that you use. I understand this is not enough detail maybe to fully grasp the details, but hopefully at least the main intuition you get. And I'm just gonna actually describe super quickly to conclude the talk and the lecture what the experiments to start trying this idea have been. We actually use chess. Chess is actually a deterministic, fully observable environment, but we made it with a small twist. And we actually use simple imitation learning, or what nowadays many people call offline reinforcement learning, to not confuse with RL algorithms and so on. So we have a massive data set of chess moves that players or people do. And then we're just going to evaluate an agent trained on these trajectories that are fixed and offline. We're going to evaluate our agent against Stockfish, against a few levels of Stockfish, which is a chess engine that is very, very good. Grandmaster level above, I'm not sure which level, but I think level 10 is already Grandmaster, I believe. So let's look first at mu0, right? This is published in the paper that I mentioned that describes mu0. And you get these kind of results. Maybe let's focus only on level 10. These are level 0, 10, and 20 of Stockfish. The higher the level, the less we win. Obviously, that makes sense. And then here we're showing if you just use a policy without search, you win sometimes with using just imitation learning, maybe like 10% of the time against level 10. But if you use more simulations, if you let this tree grow to even 1200, the amount, and it's the same policy and the same value, you're just expanding the tree search a lot, you get dramatic improvements from losing most of the time to winning a lot of the time against, let's say, Stockfish level 10. This is mu0. This is in the paper from the mu0 paper. This is just reproducing those results. Now, what happens when you say, ignore that there's another player, I'm just going to play chess as if it was a single player game. What happens is, well, not surprisingly, if you don't simulate anything, you essentially get very similar or the same results. But annoyingly, as you include more simulations, because you're so wrong about the game, this is not a game that you're playing alone, there's an opponent that you need to search over, you actually get almost no improvement and a dramatic degradation from the two-player view of mu0, right? So mu0 chess single, you see the win rate dramatically drops from 50 or whatever to essentially the baseline of not using any search at all. And it actually gets even worse the more simulations you do, because this is not, this mu0 makes some assumptions that are now not valid anymore. And then TLDR of the story is that if you use these models that treat chess as a single player game, but then use this idea that the environment is not something that is fully deterministic, but there is an opponent and it might play any move, and you use that model of the environment that is essentially using a discrete code, you essentially recover the same performance as the one that knows more about the domain, which is two-player game, planning over actions, your own actions and the opponent actions, and so on. So this kind of result is quite encouraging. And I guess in the future, maybe we'll start seeing these style approaches, because these could, in principle, be applied to StarCraft. So maybe we see finally an agent that plays the game of StarCraft or any other complex domains with a bit of model-based. This is an example on how the search works. I mean, initially, it looks over the first action, and after that is literally thinking about discrete codes or discrete transitions of this discretized state. Here we visualize the board because we can reconstruct it, but the actual engine does not, or the agent does not need to kind of reconstruct the board. This is just to show that it actually is doing what we expect it to do. So this is an interesting visualization. And then we have other results on kind of visually complex domains where we try to, again, learn this environment model that produces sort of different realizations for these kind of environments that are stochastic, where you don't see everything. So after a corridor, anything could be there, and you can see a lot of diversity being generated by these BQ style models, which are extremely powerful models of continuous or any kind of state. As you can see here, these are fairly good kind of rollouts of what could be there in the environment. So to summarize, mu0 relieves MCTS and AlphaGo from needing the ground truth environment to just modeling the transitions through this recurrent neural net of actions and opponent actions. So that is a massive improvement over AlphaGo and MCTS. And last but not least, and this is definitely not the last algorithm we see, perhaps what BQ hybrid and BQ pure does for us, which we couldn't do really before, is that now we go back to any environment we can think of in terms of complexity, partial observability, and stochasticity. We can apply this algorithm to. So that's quite exciting. So far, we tried it on kind of the perfect environments designed to work very well for these kind of algorithms, precisely to be in the worst condition scenario. And we see that we reproduce all the results. So we're quite at an exciting point of model-based reinforcement learning, in my opinion. So the point being, we need scalable model-based algorithms working across all domains. And we see a very beautiful transition, at least internally at DeepMind, of algorithms that relieve or do less and less assumptions about data and environments. And obviously, as I said, this is definitely not the last iteration of these ideas, and the community is actually exploring many, many different ideas on model-based reinforcement learning. It's a very active area of research. Still, I'm not convinced that planning is obviously necessary. It feels like it's a good idea to use planning, but at the same time, even from AlphaStar, we see that a planning-free or a model-free agent was able to play this complex domain. So maybe from the bitter lesson from Rich Hatton that says planning and learning both scale, I'm kind of convinced learning scales, but the planning part, I'm just not quite convinced myself. So maybe there's a bitter lesson after seeing kind of all the things that span off from the times of AlphaGo back in 2016 and 2017. And I will say this talk and my motivation is always based on the performance of the agent, but planning is supposed to afford many more things beyond just how well do you play the game. Thanks to a model-based approach, as I was alluding to the other day at the beginning, we can hope to achieve more transferability to a new domain or to a new reward function, or if in StarCraft there is a new balance patch, maybe if we have a model, it's going to be much easier to relearn to play the game a little bit. So these things we haven't explored, but I think it's also okay to explore raw performance, because all these things, kind of properties of model-based, for sure are going to be better if you do have an explicit model of the world. So with that, thank you for your questions, and I'm happy to stay a bit more for questions. Maybe first let's do questions on the talk, and then I can stay a bit longer, and maybe we can stop the stream to discuss a little bit about any other topics that the students of the class might want to ask me about. But yeah, thank you so much. I hope we didn't bring down Google this time, and I haven't been speaking to no one for a while. But yeah, I would be quite curious to hear your thoughts and questions, and thanks for being here, everyone.
Yep, thank you very much, Oriol. I think that everybody's still online, so Google this time received your talk. Good work.
Great.
So first, as Oriol was suggesting, do you have technical questions? And then after the technical questions, then I'll stop the streaming.
Well, if you suggest. So Oriol, one question about the VQ. As I understood, the VQ is looking for latent variables that depend on the environment, right?
Mm-hmm.
So can this be generalized as like maybe the opponent being an environment, or so like is this latent space generalizable, or is it just things that maybe are not organic, that maybe don't move, maybe don't have?
So that's probably the. I mean, it's not really the elephant in the room. With any methods, there are the caveats, and it's a very good point that essentially you're learning to map your states, right? The states of your environment that might contain a lot of rich information, and you're trying to compress these. Let's say, like in the video case that I show at the end, you try to compress all these pixels to like maybe 1 in 1,000 value, like discrete value, right? So an integer from 1 to 1,000. And right now, the way we do it is a two-stage process, where first we try to compress trajectories into trajectories of discrete numbers instead of trajectories of videos or images. And in that process, we use a loss that tries to reconstruct the images as well as possible. But indeed, these discrete latents might be focusing on irrelevant noise or irrelevant pixels, and might be actually also ignoring, I don't know, a red dot that marks where you need to go. And if it's compressing that away because a red dot in terms of reconstruction loss is irrelevant, then your representation for planning will not be that useful, because you will not imagine, oh, if the red dot was over there at the left, then going to the left is a good action, right? But now in your compressed space, you lost sort of this signal. So this is really like probably the elephant in the room. I think technically speaking, because we do the two-stage process, this is unsolvable. But if we train everything end-to-end, which obviously is always the goal, if we train these latent spaces not to compress trajectories, but rather to maximize future reward, given that we're planning with MCTS, then hopefully the representations would be aware of what matters and ignore what doesn't matter. But that's obviously like empirically always need to be validated. The size of how many, it's 1,000, is it 10,000, is it 50? There are lots of obviously trial and error as with any deep learning sort of project.
Because it's no, it sounds to me like it's kind of the transformers, like it's the kind of the idea of transformers, because I don't know how maybe if you could map the latent spaces to the environment, like theoretically, if this compression is lossless, you could map these trajectories to concrete environments, right?
Yeah, and we find, by the way, and in the BQBAE original paper, you see that these latents that are compressing an image into very few bits, if you use the decoder, because you need a decoder to train, you get the image that you wouldn't recognize, or you would see very, very small amounts of distortion, right? So it's indeed true that for the environments we tried, we compress these to like, I mean, the idea behind compressing to discrete variables is because tree search is very discrete. You need to choose. You say, okay, I'm gonna go left, and now something will happen in the environment, and the environment branches out in 100 different directions. And what you're doing is, what are the likely directions that the environment will branch? You train a language model literally over the discrete latents, and then you go on that path and you start seeing, oh, and what happens then? I take this action, and then the environment does this, and so on. But yeah, I think it's so indeed what I was showing in the chessboard is the reconstruction then from the latent back to the domain, the image or the chessboard. And in general, BQBAE is very good at compression. It's an autoencoder. It generally reconstructs very well the original signal. But then the point is that in the discrete space, because it's like transformers, like language modeling, we have a very good prior to put how transitions happen from essentially a one hot to a next one hot, which are words in a way, rather than, from these complicated pixels produce the next pixels. That's always seems to be much more difficult. So we in a way leveraging that language modeling is so advanced. So we're mapping kind of the trajectories to a sequence of words, right, of choices, and then we say, okay, and then we do language modeling on top, right? So
understood.
I guess clarified.
Interesting.
Was rushed at the end. I hope the paper hopefully will be even more clear, because I guess the homework now is, okay, like try to wrap your head around these ideas. Without the paper is probably not really possible. But apologies. Hopefully we can push it in archive or whatever soon.
Okay. So then we'll be looking at this on archive. Then I suggest that now stop the streaming, and then maybe I'll work on the career. So I'll just cover the camera, and you can assume that after I uncover the camera, it's not going to be streamed. I mean, I will stop everything, but